Imagine you're sitting in a small boat, trying to cross a river. You point your boat straight towards the opposite bank and keep rowing at the same speed. You think you'll reach exactly in front of where you started. But when you finally reach the other side, you're shocked. You've moved quite far downstream. What happened? Did you row in the wrong direction? Or the river play a clever trick? Here is the interesting part. Near the banks, the water was almost still. But as you move towards the middle of the river, the current becomes faster and faster. And then it slows down again, near the opposite bank. So here is the challenge of the day. If the boat always moves straight across the river, with a constant speed relative to the water, what path will the boat follow? And how far downstream will it finally reach? This is one of the most beautiful relative motion problems asked in IIT Advanced. And once you understand it, you will never forget the concept. So grab your pen and paper to find your answer. If you fail, do not worry, we will solve it together. Welcome back to Numericals Studio, where we try to make physics easy and scoring. Today we'll solve one of the most elegant relative motion problems using simple mathematics. Let the width of the river be d. Let's choose the y-axis across the river and the x-axis along the direction of the current. The boat moves with a constant speed v relative to the water in the y direction. Most importantly, the boat is always pointed perpendicular to the river bank. This means its own velocity has no component along the current in the x direction. The only horizontal motion comes from the flowing water itself. So, since the boat always moves across the river with speed v, we can write dy by dt equals v. Now let's examine the river current. The current is zero at both banks. It increases linearly as we move toward the center. Let's call the river's velocity u, so u is proportional to y. We can write u equals k times y, where k is a constant. At the middle of the river, when y equals d by 2, u becomes the maximum speed, w. This lets us calculate k as to w by d. So, from the bank to the middle, the river velocity is u equals to w by d times y. And from the middle to the far bank, as the current decreases again, u equals to w by d times d minus y. So the horizontal velocity of the boat depends on which half of the river it's in, giving us two separate equations. Now, switching between the ground frame and the river frame, we can see something useful. The boat's velocity with respect to ground in the x direction simply equals the river's velocity in the x direction. That gives us dx by dt equals the current speed u. And in the y direction, the boat's velocity with respect to ground is simply v. So we already have dy by dt equals v. Dividing dx by dt by dy by dt gives us two equations, one for each half of the river's velocity profile. In the first half, this gives us dx equals to w by d times y dy. Integrating this from 0 to d by 2 gives us a downstream drift of wd by 4v. In the same way, integrating the second profile from the center of the river at d by 2 to the far bank at d gives us wd by 2v minus w times d minus y whole square divided by vd. If we substitute y equals d, this simplifies neatly to wd by 2v. This way, we can see the boat's trajectory is made of two parabolic segments joined smoothly at the center of the river. And the total downstream drift comes out to be wd by 2v. Friends, you just saw how relative motion and calculus work together to explain real-world motion. If you enjoyed this beautiful problem, don't forget to like the video and share it with your friends preparing for engineering and medical entrance exams. Subscribe to Numerical Studio, where we solve challenging physics problems using concepts, intuition, and elegant mathematics. Thanks for watching, and I'll see you in the next problem.